Good morning. Thanks, Professor Ali Adibi, for the invitation. And sorry to not be present in physically, but my heart and my mind is with all of you. The atomic and gap engineering of antimonade-based type 2 superlattice for low noise, high sensitivity photodetector and imaging from deep UV up to terahertz. As we know, our eyes can see only a small part of the electromagnetic wave, 400 to 700, and we need to be able to see in the UV and at the same time infrared. And especially we would like to be able to detect exactly some of the coronavirus that creating all of the problem that we have at the present time. So for that, human vision is limited and we cannot see that. So we have to rely on technology to extend the limits further into the UV and at the same time ultraviolet region. So for that, we are mimicking the nature. The nature, our eyes and all of the sense, that they are multi-billion small sensor that give the information and through the a small exchange of the charge energy of 37 million electron volt bring the information to the brain and brain do all of the function of the processing, cognition, emotion, judgment, etc. So what we do, we tried to use the semiconductor material and especially 3,5 antimonade based equivalent to the eyes to make the focal planaries and equivalent of the brain to use the semiconductor material to have the detector. And by that to create the artificial eyes and be able to go again. Objective today again for me is to go really to the UV, extra UV, and to be able to detect again a kind of the coronavirus. So what we do, our goal is to follow the nature and at the same time to make the imager that lock our eyes to work at room temperature, doesn't need any cooling, low cost, a small size, lightweight, portable, and to have multicolor because our eyes, we have RGB, 3 color in order to see everything. So we need to have at the same time to do the technology to have multicolor with the high sensitivity because our eyes can see even one one photon. So to have this single photon detection, improve range, reduce sensitivity to weather condition, and avoid at the same time infrared countermeasure. That for that antimonade based, I would like to show that that is the best solution. So what we do, it means that if we come to colon 3,5, the antimonade base here, and to do the atomic and gap engineering with the direct and indirect gap, we can go from the deep UV up to terahertz and to make the imager. So what we need the substrate, the support, and we need the epitaxy, the difference count of epitaxy, and we need the photolithography to put all of that together, and then we come through the, again, through the quantum mechanics. If we make only the material from bulk, such as indium antimonide, in this case, the device is not going to be very efficient and it's very hard to make the multicolor. If you use epitaxy and to make the quantum well, in this case, we have the type 2, type 1, and we can do the atomic and gap engineering and to go with the difference wavelength. And now we need at the same time the photolithography in order to make, again, the small dimension, the pixel, a small pixel, in the such as the quantum dots or quantum wire with the 2-3 dimensional confinement and to make it again similar to the eyes. So for that, there are many different technology because human working out of the scientists since the decade, and that the most important part, there is the bolometer that is thermal detector, and you have that everywhere, even in your telephone and everywhere, but unfortunately is the thermal. It means that based on photon, the speed is very low. So we have the extrinsic, such as silicon, the blocked impurity band, and that is excellent, but we have to go to the very, very low temperature. But that we have the mercury cadmium telluride that is 2,6, and at the present time is the state of the art, since and multi-billion per year is going for that and is everywhere. But one of the problem is the 2,6 ionic. Mercury is very dangerous and is very expensive. So we need the technology can not only give all of the information and all of the function of the mercury cadmium telluride, but to be much cheaper, much more performance. So that is my talk that I would like to show that the antimonoid based talk to Superlattice is the only system that not only that can have all of the important parameters that we have with mercury cadmium telluride and even more. So for that, in my group, we are doing the focal planaries from deep UV up to terahertz, and all of from the different application that I'm not going to do because the today subject is antimonoid. With the indium antimonoid, that is the world first indium antimonoid of focal planaries, that when I came to the United States to Northwestern, that it was with the Lockheed and my student at the same time, Eric Mitchell, that we developed, that is the first one on this, at the same time we did on silicon and with the gallium arsenide substrate, but and at the present time is in production, but unfortunately, again, that is very hard to make the multicolor, and the function, again, is not as you are going to see that as the top two that I'm going to explain. We did again quantum well infrared photodetector, quantum dots at the same time, that is according to the theory, according to the quantum mechanics that I showed that can have excellent performance, but unfortunately there are the problem that I'm going to explain that cannot overcome all of the need that we can have with mercury cadmium telluride. So in only the top two superlattices that can have all of the information. So in this case, I am coming to see in order to make that, we have in my center all of the different necessary tools from the theory, from the material, characterization, fabrication, everything up to the system. So, and up to the camera, as you can see. So in order to make the focal planaries exactly as I mentioned to you, not only is necessary to have the excellent design, and at the same time modeling and excellent material, etc. So that in order to fabricate a focal planaries and at the same time equivalent of the brain, as I explained, to come with that is not easy task. First, we have to have the material, and we have to make the focal planaries, it means that eye spot. For that, we have the different kind. We have at least 5 photomasks, that the pixel definition, metallization, passivation, window, the opening, and all of that. And we have and after that, indium bump and the indium bump. So now what does mean? It means that we have to have equivalent, that is the equivalent of eyes. Now, equivalent of the brain, we have to have, again, exactly that, but in the transistor. So that is going to be the detector, that is going to be the transistor. So, and that, we have to have the ROIC readout integrated circuit that is equivalent of the brain and equivalent of the, again, based on the transistor electronic device. So that, again, they are the material that only this part that is coming from they have is a standard size and is not, again, most of that is classified and is not in the hand of everybody that can have. So that we bought when we are bringing the readout integrated circuit, that's only the thing that is come from outside to my group, and that when we have that now, we are going to put that we have photolithography and all of the things that I mentioned, that is 40, 60, 70 different stage, and now we have at the same time ROIC equivalent, the same design, but in order to connect them together, similar to the brain and at the same time eyes, each detector has to be in front of one transistor in the readout integrated circuit, and for that we developed the indium bomb that is, again, is what we published already, and we do the flip chip bonding, so each detector that's the FPA, that's the RIC. Each detector has to be connected to the one transistor through the indium bomb, and after that you have to remove the substrate to do the packaging, and of course the imaging. So coming to again, as I mentioned to you, if you do the quantum dots or quantum bell, that is, unfortunately, we can have, that's the QDIPS or quantum dots infrared photodetector or quantum bell infrared photodetector, and QDIPS at the same time quantum dots. We can have excellent, again, the detector, but unfortunately, as we can see, they are, again, narrowband. So only the things that can compete with the mercury cadmium telluride, again, is the bond with the top two superlattices, because the mercury cadmium telluride is a broadband, exactly as we can see here, the optical, the photo response as function of the wavelength is broadband, similar to mercury cadmium telluride. But if you look with the QWIPS and all of that, they are narrowband. So that is the reason, again, we came to the top two superlattices and comparing with mercury cadmium telluride. If you have here the band energy gap as function of the lattice parameter, here is the cadmium telluride, mercury telluride, that, as you can see, coming from the large energy gap to the very low energy gap, and they have perfectly lattice matched to each other. But one of the problem is there is no substrate on that, and at the same time, on the top of that, if you want to go to the very short wavelength, there is no, it's not possible. So, and at the same time, it's a 2-cis material. The bonding energy is very, very weak. So that becomes not only, and mercury is that dangerous. So it becomes very, very expensive and not very stable. Now, if you come to the top two superlattices, aluminum antimonide, gallium antimonide, indium arsenide, at the same time, they are or indium antimonide, they are the 3,5, and at the same time we have the gallium antimonide or indium arsenide substrate with the high quality and larger, and that the 3,5 semiconductor and is the very, very stable. So if I showed you here at the same time that is the current wavelength variation of the two detector, one based on top two superlattices, another based on mercury cadmium telluride for the 14 micron. If at 100 degrees C, they are 14 micron. When we decrease the temperature, as we can see, the variation, the wavelength of the MCT change from the 14 to come to the 20 micron, but there is no change for the top two. It means that the material is much more stable as function of temperature, something that we know. And now another part is, thanks to the top two, we have the separation of electron and hole, and with that, but by changing one monolayer, we can change at the same time the wavelength, but with the same effective mass, that the large effective mass give much less dark current, and especially at the long wavelength, much better performance. So all of that is the many advantages of the T5 and the top two by comparison to mercury cadmium telluride. So here I'm showing you now. You have here, again, that's the indium arsenide, gallium antimonide. As you can see, the conduction band of indium arsenide is the lower energy than the valence band of the gallium antimonide. So if we put them together, we have the separation of the electron and hole. And we have aluminum antimonide, large band gap at the same time, that you are going to see that we are going to use it as a band gap engineering to go from deep UV up to TRS. So now, in order to make, again, the difference wavelength, we use the difference technique, difference modeling method, that is the KP model and tie banding model. That is the two that we are using, and at the same time the difference method, in order to come to have the design of the structure for the detector, any wavelength that we want. Each method has some advantages and disadvantages. KP model is much the simpler and less parameter, and that fast calculation that we do that, especially for the long wavelength material, long wavelength at the same time. And the disadvantages is only valid near brilliant zone center and cannot predict the strain effects when we have this material in the larger, as an example, gallium antimonide, and the difficulty for short period superlattices, and cannot model interface effect. But if we go to the tall banding model, empirical tall banding model has many advantages: calculate the band structure within the entire brilliant zone, model different interface effect in a superlattice, can model the short period superlattice, can predict a strain effect, and at the same time more accurate in general. But the disadvantages is, of course, we have a lot of different parameters, especially we can have 15 if we come with the sp3 and at the same time the spin orbit effect, the coupling, and at the same time needs a large size of Hamiltonian, but that we can manage. And exactly as you can see here, if I come the indium astronaut and indium antimonide, exactly as I mentioned, if I keep the one of the material fixed and they change the another one with the 1 or 2, here we have the brilliant center of brilliant zone. As you can see, not only with 1-2 monolayer chain we can change the gap, but at the same time we can change intergap, interband at the same time, eliminate Auger as an example, and to have all of the best with the for the same wavelength, we have many different ways in order that to optimize the structure, opposite to mercury cadmium telluride, that for any wavelength we have only one possibility. And here, as an example, if I want to have the 11 micron on antimonide, gallium antimonide substrate, so I can have exactly the difference, optimize the difference parameter, and to give exactly theoretically to say that what I need in order to have this wavelength. Now we have that immediately. That's the growth. We can do that. We do it in the boards MWIR and MOCVD, and that we do that. It's the MWE, and that you can see here, that is the structural atomic force microscope X-ray, that's showing that we can control atom by atom. And now, so as the new material, we started to come with the long wavelength material for the focal planaris. And the importance of the long wavelength, because that is the part that mercury cadmium telluride has a lot of difficulty, because due to the big the mercury atom, that is that the material are not very stable. And the effective mass is very low, exactly as I mentioned. So we try to optimize here. You can see that the mini arrays of the antimonide based, that the three important parameters, the responsivity, quantum efficiency, and detectivity. As we can see here, at 77K in backside configuration, and that this oscillation is related to the oscillatory fringes from the backside illumination, the backside illumination, and this result show that at 11 micron already, with the very thin structure on gallium antimonide substrate, it compared to the very sophisticated and the thick buffer of the mercury cadmium telluride, that is, this result is equivalent to the best of mercury cadmium telluride. Now, coming to the mid wavelength again 3 to 5 micron, and comparing again with the mercury cadmium telluride, that is the 60-70 years old technology. And that we can see here, detectivity as function of wavelength for the difference temperature, and blip temperature is here about 195, which with the 300K background and the 2 pi field of view, and that is equivalent to the best, again, as we can see here, that's the dark current, and that's the R0A, and that is the best comparing apple by apple with the mercury cadmium telluride, to show that yes, that this material can compete with the best of mercury cadmium telluride with much less, much thinner, and much cheaper, and much simpler structure. Now going to the short wavelength. The short wavelength, again, how we can come with this material of the gallium antimonide, indium astronaut, to go to the short wavelength. I mentioned how we can go to the long wavelength, but the short wavelength, again, by doing the atomic atomic and gap engineering to put a few monolayer of the aluminum antimonide inside the gallium antimonide, that we can say that, okay, that is the log AM, we say MS structure, and we can see that by that we can increase the gap and to go to the short wavelength material. And here is the, again, the just recent result to show that thanks again to NASA, thanks to the NASA, and at the same time the DOD, that we can see here the detectivity at room temperature with the bias voltage of 20 millivolt from the 0.4 UV up to 2.4, again, the cut on and cut off. At 300K, the detectivity is 2.6 times 10 to the 10 under minus 20 millivolt, and at 150 is 5.6 times 10 to the 13. That is the excellent result. Not only is the world first, but at the same time, excellent result demonstration of the antimonide top 2 for that. So we did all of that. We demonstrated for the top 2, for the short wavelength, mid wavelength, long wavelength, and at the same time, different focal parents for the first time, 1K by 1K for the long, and at the same time the mid, short, and all of that. But the problem was to say that when we make this material at the interface is very important, because the interface is not, we have the gallium antimonide, first of all, in order the lattice mismatch, so at the interface, the indium antimonide or the gallium arsenide type, so we have to do some engineering in order to have lattice match. That is the one part, and gallium antimonide at the same time is always p-type, so there is a kind of defect that they say that, okay, should get rid of the defect, and that is create the problem again, high dark current, high dark current in this material. So that but they say that is not easy to do for the production, especially when we go to the MBE and we need to have the 1,000 and 1,000 mono layer and very thin layer. That is that. So we came with the following in order that to eliminate all of the problem with the gallium antimonide top binary, and to come with the gallium free top 2 superlattice. Indium arsenide, antimonide, aluminium arsenide. What is the problem of the gallium? Okay, if you come here, that you can see here, we have indium arsenide, indium antimonide. So if we have indium arsenide, antimonide, that is the top 2 again, and at the interface, we have only to change one the element, only antimonide, in order to go from the, again, the PUV up to terrestrial. But the problem was that in the literature, there are some group they work, and the theoretical, they say that is impossible in this material to have high, we can have low dark current, high, but is very important is that we cannot have high quantum efficiency. And that it was the things that we tried to demonstrate that is not true, and we can do it. So what we did is the following. With the indium arsenide, antimonide, in order to change the wavelength, is important to make the thickness of the indium antimonide very short. So we can come and to short that. And when we come to the standard, however, when the indium antimonide cannot play at the same time like a good barrier in order to have the good devices. So what was again what we did, we came with the atomic and gap engineering. It means that inside of each indium arsenide or gallium antimonide, we try to insert a few monolayer of aluminum arsenide antimonide. Exactly. That we say that is H structure. So as we can see here, that is the barrier wide band gap, and that is the low band gap. So by that, we try to do, again, for the indium arsenide engineering, again, that the structure that we were growing here, it was for 9 micron, and by inserting the indium and aluminum arsenide antimonide, it will come about the 1.8 micron. So what we did, we tried in the both cases to demonstrate the imaging. That is the mid-wavelength infrared and long-wavelength infrared. Again, that it was the world first. That is with my student, Pierre Delaunay, that now he's a big boss at Atlantic Aerospace and developing all of this technology, that we went at them. Now we demonstrated that in the gallium-free as well. Now we come to the 1K by 1K, that is at the 11 micron. That's the big problem of the mercury cadmium telluride. So we did that again with the antimonide base with the excellent performance that had, and we gave again to Dr. John Hobb from the Air Force, that he is expert in the focal planaries, my mercury cadmium telluride and that is this paper. He is at the same time the co-author to say that the performance is excellent of the equivalent to the best mercury cadmium telluride with much better performance and much cheaper and much easier. So now we try to do at the same time long to short on gallium arsenide, and we can do that at the same time on silicon substrate with the excellent performance. Now, today, multicolor, because our eyes again is a multicolor, and we need, if we have the detector or imager with the two band, if we have only one band, mid or long, that we can see or this one or this one. But if we have the both together, we can see again much better performance. So that it was again the things that we did. We tried to come again for the first time in the board, thanks to the excellent again the student. At the same time, we did the mid-wavelength long with the 13 micron, 9.5 micron, and 81 degree K. That, as you can see here, that is again another of my students, the Ed Huang, that now he has his own company, but working. So that it was again world first demonstration, and now we have this result in the gallium-free aspect. Now we can, for the long mid, 1.3 to 13 micron and 5.5 micron. Why is important? As you can see on the same layer, same image, by only changing the voltage, and at the same time we can see that 5.3, 13 micron, that's again the world first, the two color with the mid format that we have in the gallium free at the same time, and exactly at the we published 2012, but even today they are again the unique result, and we have in the gallium free the same now. Now we go to the mid-wave with short wavelength, because we need at the same time short, mid, active, passive. So the same way, by doing again the atomic gap engineering to calculate exactly and to fabricate, to do the material, to do the fabrication. And as you can see here, that is the result in the two color world first again for the mid format at the 4.5 micron and 2.2 micron. Exactly. Now we have this result with the gallium free in a much better performance and higher temperature. So now here exactly we can see that what's the difference, because in the shorter wavelength, that is the active imaging, in the long wavelength is the passive imaging, as we know. Now that is historically, the ideas came 1971 by Leo Ezaki and at IBM, and they demonstrated by MBE. Many different groups around the world, they tried to work in United States and in Fraunhofer, everywhere, the great group, but nobody could make the focal planaries. And it was that during the conference exactly of SPIE that I was giving the talk, that Dr. Gail Brown was the chair of the session. He mentioned that, but in this material, nobody can make the focal planaries. That it was the things that we did exactly the same time with the material, and that is one of my students. Again, he is at L3, and that immediately Dr. Mehmet Tidro from the army, that he came and he saw that. They immediately, she took that, and after that with at army with Fenner Milton, that they put the VISTA program, but that we continue with all of that Northwestern in my group, one by one. We tried that all of the students that you can see one by one, they try to have the different wavelength, different performance, and they transfer the technology to the different again a part of the country, and they are all of them again, all of that is continuing. Now, one of the things that it was very important that we demonstrated, it was again with the part of the PhD of Pierre Delaunay that he did, and the material at the same time the focal planaries is went through the MIT Lincoln Lab and the difference, the Lockheed and the difference group, and they demonstrated in the system that for the correctability and long stability, comparing mercury cadmium telluride with the top 2 focal planaries at 9 micron, 10 micron with the indium antimonide, demonstrated that the 2-point non-uniformity correction is more efficient for top 2 than mercury cadmium telluride, or if we have the stability is much longer for top 2 by comparing to the indium antimonide. It is longer than 25 hours for top 2 and about 1 hour for indium antimonide, and at the same time it is also significantly better than a quadratic correction for MCT. The time stability for MCT is only 5 minutes. So you can see again, and that this technology, thanks again to the work of the difference group, and especially at NASA, at the group of Dr. Murzi Jablabo, that he is expert and he is at the same time one of the person that's supporting some of our activity at the person. And he tried in their group, they put that in the International Space Station and change, and is continuing. Now they are much better imaging, much better performance, and at the same time much cheaper. So by that, I would like to say that the timeline of antimonide, that when they started for the first investigation of indium antimonide, and at the same time nobody could believe, and I was insisting that that is the future. And as you can see up to now, everything that we demonstrated and then continue to change again, that is change the technology of the imaging to make it much better, more performance, much cheaper, much affordable, and now is going to be again, that's the future. And thanks for your attention. I wish all the best for you. Please don't forget again, www. It means that wash your hand, please put the mask, and at the same time separation from each other. Be very careful and work all of us together for this kind of activity, this kind of the device, to see that how we can detect the virus, and especially in the UV part, the coronavirus, and how we can eliminate that at the same time. Thank you.